Hello, welcome to a video about limits and infinity. Um, yeah, calculus, it's just all about infinity. So we're just going to start here and basically never stop talking about things that are infinitely large or infinitely small. We are going to start this video talking about three cases where limits don't exist. One of those cases is when we have an absolute value, which really acts like a piecewise function. So I am going to rewrite this as x minus 3 over the absolute value of x minus 3 and drop the absolute value for whenever x is greater than 3, because when x is bigger than 3, I don't need the absolute value. Then I'm going to rewrite it as x minus 3 over negative x minus 3 for when x is less than 3, because when x is less than 3, the absolute value negates the negative to give us a positive answer. So if I want to simplify that even more, it becomes 1 for when x is greater than 3 and negative 1 for when x is less than 3. So if I want to evaluate the two-sided limit as x approaches 3, it's going to 1 from the right of 3 and negative 1 to the left of 3, which means I don't know which way it's going. So this limit doesn't exist because this is a function that has steps. Now, in number 2, if I try to plug in 2 for x, I have 2 plus 3 over 2 minus 2, which is 5 over 0. 5 divided by 0, I'm thinking this limit doesn't exist, and it doesn't, because I have a non-zero number divided by a 0, so it's highly unlikely that I can try to factor, cancel, uncomplexify. I don't think there's anything I can do. But mathematicians don't really like it when we just say it doesn't exist. We always want to know more. So if I look at this as x approaches 2 from the right, and I look at what happens to that, my numerator is 5-ish. I'm not using an equal sign because I'm just thinking right now. And my denominator is 0-ish, but it's 0-ish in a positive kind of way, because if I'm greater than 2, 2 minus 2, but instead 2.01 minus 2 is close to 0 but positive. So 5 divided by a number close to 0 but positive is going to be positive infinity. And if I do the same thing and x approaches 2 from the left, I still have 5-ish, but now I'm plugging in a number to the left of 2, like 1.99, and 1.99 minus 2 is 0-ish, but negative. And so if both of those things are true, I then have negative infinity. So from the right, I'm going to positive. From the negative left, I'm going to negative infinity, which means that this limit doesn't exist. And as a matter of fact, if I think about this as a rational function, that means that I have a rational function with a vertical asymptote at 2, where on one side of the asymptote it goes up, and on the other side it goes down. And then last but not least, another way for a limit to not exist is, what if I thought about the sign of infinity? Well, the sine function just does this forever. And so as x approaches infinity, that sine function is oscillating between 1 and negative 1 and everything in between for eternity. So the limit as x approaches infinity does not exist. But again, as a mathematician, we'd probably say, well, how doesn't it exist? It doesn't exist because sine oscillates between 1 and negative 1. Okay, now, what if I keep letting x approach infinity and I figure out what happens then? Well, if x approaches infinity in a rational function, you may have learned before that if x goes toward infinity, you can highlight the highest powered terms, and if the degree of those terms match, then your limit is equal to the ratio of the lead coefficients. So that would be 5 over negative 4. Now, that's just a rule. Why? Well, the why here is pretty fun. It's what I call the spit in the ocean rule. Because if you're rowing out on a boat and you spit over the side of the boat into the ocean, well, you shouldn't row in the ocean. Maybe don't row in the ocean, okay? But still, if you're on a boat and you spit into the ocean, does the ocean now have more water in it? Technically, yes. But does anybody care? No, we don't care. There's tons of water in the ocean. Your spit is not going to make a difference. Okay? So, what does that have to do with math? Well, it has to do with math like this. If I take the limit as x approaches infinity of 5x cubed minus 2x plus 9 over, I'm going to rewrite this as negative 4x cubed plus 6, I have infinity. And then I'm cubing it. I am multiplying 3 infinities together. I have an infinite number of infinities and then an infinite number of that. And then that times 5. That is so gigantic that I don't even care that I'm subtracting 2 infinities away. I don't even care that I'm adding 9. Nobody does. Same thing down here. I don't care that I added 6. That's just silly. And so this original limit is equal to the limit of just the highest power or fastest growing terms. And then I can look at that and say, well, when I'm evaluating these limits, I can cancel out those x cubes. And now this is the limit as x approaches infinity of 5 over negative 4, which is 5 over negative 4. Okay. Then when I come over here to number 2, I'm going to do the same thing, but faster. So if x is approaching any kind of infinity, you're just going to isolate the highest powered terms and say this is really the limit as x approaches a negative infinity of 5x to the 4th over negative 4x cubed. X cubed and x to the 4th leave an x. And so if I have 5x over negative 4 and x goes to infinity, I have negative infinity over negative 4, which is positive infinity. And if you're thinking, yeah, but can't I just do the thing where if the top is bigger than the bottom, then it goes to an infinity? Yeah, you totally can. But my job is to explain to you why that works. Coming down here, as x approaches infinity, I can look at the highest powered terms and say this is equal to the limit as x approaches infinity of 5x cubed over negative 4x to the 13th. Simplify that down to x to the 10th, which means I now have the limit as x approaches infinity of 5 over negative 4x to the 10th. And as x goes to infinity, that's 5 divided by negative infinity. 5 divided by a ginormous number is teeny tiny. So this goes to 0. Does it matter that it goes to 0 from the negative side? Nah, 0, 0. And then if you have a square root, fun fact, the square root of x squared is identical to the absolute value of x. So when I keep only the highest terms of this one, I have the limit as x approaches infinity of 3x over the square root of 2x squared, which is the same as 3x over radical 2 times the absolute value of x. And since x is approaching positive infinity, this x and that x are the same thing, so they divide to 1, and I'm just left with 3 over radical 2. Now, what does that all mean? Well, when you look at x as it increases or decreases without bound, when you evaluate a limit like that, you result in the end behavior of a function. What's happening all the way to the right or all the way to the left. When the limit results in a numerical value, it can be said that the function has 1 or 2 horizontal asymptotes. There can be 2 horizontal asymptotes. It happens more often than you think. Okay? So if you are asked to test for horizontal asymptotes, the line y equals b is a horizontal asymptote if either the limit as x goes to positive infinity or the limit as x goes, to negative infinity equals b. Okay? That means you always got to look at both. If you are asked to find horizontal asymptotes, you take the limit as x approaches infinity, you take the limit as x approaches negative infinity, and if either or both of those yield a singular numerical value, that's your horizontal asymptote. If you are trying to evaluate the end behavior of a rational function, that's polynomial divided by polynomial, you can make some generalizations. Those are the ones we talked about before. If the degree of the numerator and the denominator are equal, then the horizontal asymptote is y equals the ratio of the coefficients. You may notice that I skipped over some words there. This works for more than just rational functions, and we'll get to that in a minute. If your numerator and denominator have the same growth rate, is another way to say that. Then you take the ratio of the coefficients. If the degree or growth rate in the denominator is greater than the growth rate in the numerator, so if the bottom is bigger than the top, then you have y equals 0 as a horizontal asymptote. And if the degree of the growth rate in the numerator is greater than that of the denominator, if it's bigger on top, then there is no horizontal asymptote. But there may be a slant asymptote. Okay. So now let's just look at a couple. Other horizontal asymptotes. So here are non-rational functions. What do? Well, if we want to find the asymptotes for these, I'm going to take the limit as x approaches infinity and the limit as x approaches negative infinity and evaluate them separately. So 2 over 1 plus e to the x minus 1. Well, let's see. If I plug in infinity for x, I'm going to just do my nebulous work off to the side here. If I plug in infinity, I have 2 over 1 plus e to the infinity minus 1. Well, e to the infinity is gigantic. 2 divided by a gigantic number is 0. 0 minus 1 is negative 1. So y equals negative 1 is one of my horizontal asymptotes. Now let's see what happens as x approaches negative infinity. Oh, I didn't mean to write that. I meant to write the x there. And that negative infinity over here. Sorry. Well, e to the negative infinity means 1 over e to the infinity. And 1 over e to the infinity, I'm running out of space here. So I'll just write it here. That's going to be like 0. So 2 over 1 plus 0 is 2. 2 minus 1 is 1. Y equals 1 is another horizontal asymptote. So if I pull this up on a calculator, I have 2 divided by 1 plus e to the x minus 1. And if we graph it, you can see that there are 2 horizontal asymptotes there. All right, couple more. I believe this is supposed to say cosine x. Sometimes OneNote eats my things. So now let's see what happens as x approaches infinity when we have trig. So there's x approaches infinity. Here's x approaches negative infinity. Well, we said as x approaches infinity, sine, and honestly cosine, bounces between 1 and negative 1. So the limit of those didn't exist. That part's true. But here's the thing. This is going to bounce between 1 and negative 1, but that thing's still going to infinity. We have a spit in the ocean rule, where if I want to bring up a terrible analogy, I have 3 times infinity. I have the ocean. And then I'm adding something between plus and minus 1. So it's like you're hanging over the side of a boat with a straw and sucking in some of the water from the ocean and then spitting it back out and sucking it in and spitting it back out. Nobody cares. It doesn't make a difference. So I can ignore this. And I can ignore that. And if I have 3x over 2x, they have the same growth rate. So as x approaches infinity, I'm going to take the ratio of their coefficients. So y equals 3 halves is one horizontal asymptote. Well, the same thing applies for negative infinity. These still bounce between 1 and negative 1. Then 3x over 2x, the x's still divide to 1, leaving me with 3 halves. And I have exactly one horizontal asymptote at y equals 3 halves. So let's look at that one. I'll use the fraction button here. So it was 3x plus sine x over 2x minus cosine x. And there we go. It looks like I crossed that horizontal asymptote, but it's there. Okay, now I have this absolute value again. So if I'm taking the limit as x approaches positive infinity, that numerator is going to be positive. So I'm just going to write it like this. And if x approaches negative infinity, that numerator, the interior part, is going to be negative. So the absolute value would negate it. And then I just look at these with my rational function eyes. I ignore anything that's not the highest power term. 2x cubed over x cubed as x approaches infinity is 2. Same thing here. If I distribute that negative, I would have negative 2x cubed and positive 9. Ignore everything except for the highest power term. Now I'm landing at negative 2. So I have 2 asymptotes at plus or minus 2. And then last but not least, as x approaches infinity, sine x over x, and negative infinity, sine x over x. Well, as x approaches infinity, my numerator is sticking between plus and minus 1, and my denominator is going toward infinity. So I have plus or minus 1 divided by infinity. This is heading towards 0. As a matter of fact, this is also heading towards 0. But I want to graph this one because this one has the coolest asymptote of all. My x didn't show up. There we go. This one crisscrosses over the asymptote for a long time, and it's super neat. Look at that. That's an asymptote that you cross an infinite number of times. Still an asymptote, though, because it's still following y equals 0. Okay, so I normally end with a joke. I'm going to end this with my favorite joke of all. What color socks does a bear wear? What color socks does a bear wear? Bears don't wear socks. They have bare feet. Have a great day. Bye now.